Welcome! In this session, we'll dive into the problem titled Append k integers with minimal sum. Together, we'll explore the core problem statement, break it down, and analyze different approaches to solve it effectively. Let's get started. In this problem, you are tasked with appending a specified number of integers to a list in a way that minimizes their sum. You are given an array of integers, nums, and an integer k. The goal is to consider the set of positive integers that do not already appear in nums and identify the first k integers from this set. Once these integers are identified, you append them to the list and calculate their sum. The input includes the array nums, which can have up to 100,000 elements, and the integer k, which can be as large as 100 million. The output is a single integer representing the sum of the first k missing positive integers. Let's explore an example to see how this works. For the first example, the input nums is 1, 4, 25, 10, 25, and k is 2. The task is to find the first two missing positive integers that do not appear in nums and compute their sum. The set of missing positive integers starts as 2, 3, 5, 6, 7, 8, 9. Here, the first two integers from this set are 2 and 3. Adding these together gives the sum 2 plus 3 equals 5. Therefore, the output is 5. Now, let's examine a second example to further clarify the process. In the second example, the input nums is 5, 6, and k is 6. The set of missing integers is 1, 2, 3, 4, 7, 8, 9. The first 6 integers from this set are 1, 2, 3, 4, 7, and 8. Adding these values results in the sum 1 plus 2 plus 3 plus 4 plus 7 plus 8 equals 25. So, the output is 25. It's important to note a few constraints here. The array nums can have duplicates, but these are treated as a single occurrence when identifying missing integers. Additionally, for very large values of k, we need an efficient approach to compute the result without explicitly generating all missing numbers. The solution must also handle scenarios where k exceeds the range of integers in nums, smoothly transitioning into numbers greater than the maximum value in nums. To tackle this problem, we first considered a brute force approach. The intuition here is straightforward. We repeatedly identify the smallest positive integer that's missing from the input array nums, append it to the list, and continue this process until we've appended k integers. To implement this, we can use a set for quick lookups, allowing us to determine missing integers efficiently. However, the core challenge of this approach is its inefficiency. Iterating over all positive integers to find the missing ones becomes computationally expensive, particularly when k is large or the array nums has many elements. Analyzing the complexity, the worst-case time is proportional to the product of the number of integers we check and the size of the array, which makes this approach impractical for larger inputs. As a result, we need to focus on more efficient methods to solve this problem effectively. To improve on the brute force method, we adopt an optimized approach that combines sorting and mathematics to systematically find the missing integers. The key idea is to leverage the structure of a sorted array to identify gaps between consecutive elements, which represent the missing numbers. To implement this, we start by sorting the input array and removing duplicates using a set. Then, we initialize variables to track the sum of the missing integers and the next smallest positive integer we're looking for. As we iterate through the sorted array, we calculate the range of missing integers between the current number and the next expected value. From this range, we append the required number of missing integers to reach our target k, summing them as we go and updating our counter. If we exhaust the array and still have integers to append, we calculate the remaining values beyond the maximum element of the array. This structured approach ensures we efficiently find and sum the required integers without unnecessary computations. Sorting the array provides an efficient way to locate gaps between consecutive elements, which is crucial for identifying missing integers. Additionally, we can optimize the summation process by using the formula for the sum of the first n integers, n plus 1/2, to avoid iterating through numbers unnecessarily. This means we can quickly calculate the total for a range of integers without explicitly summing them one by one. Once we've appended enough integers to reduce k to 0, the process naturally terminates without further computation. The complexity of this approach is dominated by the sorting step, which is O, n log n, and the subsequent iteration through the array is linear, making the overall complexity O, n log n. The space complexity remains manageable at O, n, as we only need to store the sorted array and the set of unique elements. This method balances efficiency and clarity, making it a strong candidate for solving the problem effectively. When comparing the two approaches, the trade-offs become clear. The brute force method is simple to implement and easy to understand, but it suffers from severe inefficiencies when handling large inputs due to its repetitive checks for missing integers. This makes it unsuitable for competitive programming or real-world scenarios where performance is critical. On the other hand, the optimized approach is slightly more complex to implement but vastly superior in terms of efficiency. By sorting the array and systematically identifying gaps, we avoid unnecessary computations. The use of arithmetic formulas further streamlines the process, eliminating iterative summation. Ultimately, the optimized approach strikes an ideal balance between clarity, efficiency, and scalability, making it the preferred solution for this problem. To solve this problem, we need to find the k smallest positive integers missing from an unsorted array nums. The array may contain duplicates, and the goal is to return these missing integers in ascending order. The first step in our algorithm involves setting up the necessary data structures. We use a set to store all elements from nums. This allows for extremely fast lookups, ensuring we can efficiently check if a number exists in the array. Additionally, we prepare a list to store the missing integers as we find them. Finally, we initialize a variable called candidate to start checking from the number 1. This setup ensures that we can sequentially identify the smallest missing integers while maintaining efficiency. Once our setup is complete, we proceed to find the missing integers. We begin with candidate set to 1 and continue iterating until we have identified exactly k missing integers. For every number we check, we determine whether it is present in our set of nums. If it isn't found, we append it to our list of missing integers. If it is found, we simply move on to the next number. After every check, the candidate is increment, ensuring the search progresses sequentially through positive integers. For example, given the input nums equals 2, 3, 7, 11, and k equals 5, we first convert nums to a set for fast lookups. Starting with candidate equals 1, we find it isn't in the set, so we add it to our missing numbers list. We then check candidate equals 2 and candidate equals 3, which both exist in the set, so we skip them. For candidate equals 4, it's missing, so we add it to our list. This process continues until we collect 5 missing numbers. Continuing from the same example, after adding 4, the next check is for candidate equals 5, which is also missing, so it's added to the list. We then check candidate equals 6, which is also missing, and candidate equals 8, which is missing as well. At this point, we've identified the 5 missing integers as 1, 4, 5, 6, 8. The algorithm stops once we've reached the required count of k missing integers, and the result is returned. This approach ensures that we always find the smallest integers first, and the use of a set guarantees that our lookups are efficient. Key insights from this process include the importance of sequential search to prioritize smaller integers, breaking the loop as soon as we reach k results to save computation, and handling edge cases. For example, if nums is empty, we simply return the first k positive integers. If nums contains numbers up to a certain limit but k exceeds the gaps, the algorithm naturally continues beyond the range of nums to find the additional numbers. Analyzing the complexity of this algorithm shows why it is efficient. Constructing the set from nums requires O, n, time, where n is the size of the input array. Finding the k missing integers involves iterating through numbers starting from 1. In the worst case, the algorithm may need to check up to n plus k numbers, resulting in an overall time complexity of O, n plus k. For space complexity, the set used to store nums takes O, n, space, and the list of missing integers requires O, k, space. This gives a total space complexity of O, n plus k. Optimizations include early termination, where the loop stops as soon as k integers are found, and the use of efficient data structures like a set for constant time lookups. Additionally, the algorithm uses minimal extra space, relying only on the set and list, making it both time and memory efficient. The solution to the problem begins by sorting the array nums and removing duplicates using set and sorted. This ensures we have a unique and ordered list of numbers to work with. Next, we initialize total_sum to keep track of the sum of the minimal missing integers and current to indicate the smallest positive integer we are currently considering. The primary goal is to add the k smallest integers not present in nums. We loop through the sorted nums array. For each number in the array, we check if there are missing integers between current and number. If so, we calculate how many of these missing numbers we can add, bounded by k, and compute their sum using the formula for an arithmetic sequence. The total_sum is updated accordingly, and k is reduced by the number of missing integers added. The current pointer is then updated to reflect the next integer to consider. If k becomes 0 during this process, it means we have added all required missing integers, and we return total_sum. After processing all numbers in nums, if there are still missing integers to add, i.e., k greater than 0, we compute the sum of the next k integers starting from current and add it to total_sum. This handles the case where we need to append integers larger than the largest number in nums. Finally, the function returns the total_sum as the result. This solution efficiently handles the problem by combining sorting, arithmetic sequence calculations, and logical traversal of the input array. Here we start by importing the necessary packages and defining the solution class. Inside our method, minimalKSum, we use a tree set to store the integers from the input array nums. The tree set not only removes duplicates but also keeps the numbers sorted in ascending order. This is important because we need to process the numbers sequentially. Next, we initialize two variables, total_sum, which will store the cumulative sum of the appended integers, and current, which keeps track of the smallest number we can add to the sum. We then iterate through each number in sorted nums. For every number, we first check if there are any missing numbers between current and the current number in the set. If there are, we calculate how many of these numbers we can add using the math.min function, ensuring we don't exceed the remaining count of k. The sum of these missing numbers is calculated using the formula for the sum of an arithmetic sequence, and this value is added to total_sum. We then decrement k by the number of integers we added and update current to reflect the next number to process. If at any point k becomes 0, we return total_sum since we've completed appending the required numbers. Finally, after processing a number from the set, we ensure that current is updated to the greater of its existing value or the next number after the current number in the set. Now, after processing all the numbers in the tree set, there may still be some values left to append if k is greater than 0. In this case, we simply use the formula for the sum of an arithmetic sequence once more to calculate the sum of the next k smallest integers starting from the current value of current. This sum is then added to total_sum. Finally, we return total_sum, which contains the minimal sum of the k appended integers. This approach ensures efficiency, as we leverage the sorted nature of the tree set and avoid redundant computations, while the use of arithmetic sequence formulas helps to handle multiple numbers at once without looping over each individually. To solve this problem, we start with the input array nums equals 1, 4, 25, and k equals 2. First, we sort nums to get the unique sorted array 1, 4, 25. We initialize two variables, total_sum, which will store the sum of the missing integers we add, and current, which tracks the next integer we need to consider, starting at 1. Now, looking at the first element of nums, number equals 1, we see that current is equal to number, so there are no missing integers between current and number. We simply update current to the next number after number, which is max, current, number plus 1, resulting in current equals 2. Moving to the next number, number equals 4, we observe that current is less than number, which means there are missing integers between them. Specifically, the numbers 2 and 3 are missing. Since k is 2, we can add both missing integers. We compute their sum using the formula for the sum of the first k integers starting at current, total_sum plus equals count asterisk, 2 asterisk current plus count 1, // 2, which evaluates to 5. We then update k to k count, reducing it to 0, and set current to current plus count, which becomes 4. Since k is now 0, we stop and return the total_sum, which is 5. For the next example, we have nums equals 1, 2, 3, and k equals 5. After sorting nums, we get 1, 2, 3. We initialize total_sum to 0 and current to 1. Looking at the first number equals 1, we find that current is equal to number, so there are no missing integers between current and number. We update current to max, current, number plus 1, which makes current equals 2. Similarly, for the next number equals 2, there are still no missing integers since current is equal to number. Again, we update current to number plus 1, making it 3. Finally, for number equals 3, we see the same situation, no missing integers between current and number. We update current to 4. At this point, we have processed all elements of nums, and k remains 5. This means we still need to add the next 5 integers. Since k is greater than 0, we now add the next k integers starting from current, which is 4. Using the formula for the sum of the first k integers starting at current, we compute total_sum plus equals k asterisk, 2 asterisk current plus k1, // 2. Substituting the values, we get total_sum plus equals 5 times open parenthesis 2 times 4 plus 5 minus 1 close parenthesis // 2, which evaluates to 40. This completes the process, and the final output for this example is 40. For the next example, nums equals 10, 20, 30, and k equals 3. We start by sorting nums to get 10, 20, 30. We initialize total_sum to 0 and current to 1. Now, we process the first number in nums, number equals 10. Here, current is 1, which is less than number, meaning there are missing integers between them. Specifically, the integers 1, 2, 9 are missing. Since k is 3, we only need to add the first 3 of these missing integers. We calculate their sum using the formula total_sum plus equals count asterisk, 2 asterisk current plus count 1, // 2, or count as min, k, number, current. Substituting the values, count equals min, 3, 10 to 1, equals 3, and the sum evaluates to total_sum plus equals 3 times open parenthesis 2 times 1 plus 3 minus 1 close parenthesis // 2, which equals 6. We then update k to k count, reducing it to 0, and set current to current plus count, making it 4. Since k is now 0, we stop here and return the total_sum, which is 6. To analyze the time complexity of the solution, we start by looking at the different operations involved. First, we convert the input array into a set to remove duplicates. This operation takes n time, where n is the size of the input array. After deduplication, the unique elements are sorted, which has a time complexity of m log m, where m represents the number of unique elements in the array. Next, we iterate through the sorted unique elements, and while the loop itself runs in m time, the inner operations such as using the arithmetic sum formula and updating variables like current and k are performed in constant time, 1. Finally, if there are still numbers to append after the loop, the arithmetic sum formula is again used to calculate the sum of the remaining integers in 1 time. These steps collectively define the individual contributions to the algorithm's time complexity. When we combine these steps, the overall time complexity can be expressed as n for deduplication, plus m log m for sorting, plus m for iterating through the unique elements, and 1 for the final sum calculation. Since the number of unique elements, m, is always less than or equal to n, the time complexity simplifies to n log n. Moving on to space complexity, the solution requires space for the set used to store unique elements, which takes m space. Additionally, the sorted version of these unique elements also requires m space. Beyond this, the algorithm uses only a constant amount of auxiliary space for variables like total_sum, current, and k, which amounts to 1. Therefore, the overall space complexity is m, which in the worst case is n, since the number of unique elements cannot exceed the size of the input array. Let's compare this optimized solution to a brute force approach. In a naive solution, we would iterate through all integers starting from 1, checking if each integer is missing from the input array, and appending it if necessary. This would involve iterating over up to k missing integers and performing a linear search for each integer in the input array, which takes n time per check. Consequently, the overall time complexity of the brute force approach becomes k*n, making it highly inefficient for large values of k and n. This highlights the inefficiency of redundant checks and the lack of leveraging sorted missing numbers in the brute force method. The optimized approach resolves these inefficiencies by sorting the input array once and processing only the unique elements, which reduces the time complexity to O, n log n. Missing integers are calculated directly using arithmetic formulas in O(1) for each segment, making the solution significantly faster than the brute force O, k*n, particularly for large inputs. Now, analyzing the best, average, and worst cases, we observe that the time complexity remains O, n log n in all scenarios. In the best case, even if the input array is empty or contains no duplicates, sorting still takes O, n log n. In the average case, the algorithm processes m unique elements and calculates the sums for missing numbers efficiently. In the worst case, when all elements are unique and scattered, the algorithm still processes all n elements, but the time complexity remains O, n log n. Thus, this consistency makes the solution robust and scalable for various input sizes. When solving this problem, there are a few common mistakes to watch out for. First, not accounting for duplicates in the input list nums can lead to incorrect results. For example, if nums contains 1, 1, 2, some solutions mistakenly treat these duplicates as separate numbers. The simple fix here is to use a set to track unique elements and avoid double counting. Another frequent issue involves inefficiently searching for the smallest missing integers. A brute force approach that repeatedly checks numbers from 1 upwards can easily result in O, n*k, complexity, which is far from optimal. Instead, you can adopt a more efficient strategy, such as using a Boolean array to mark numbers or leveraging mathematical properties. Lastly, edge cases involving k often trip people up. For instance, if k is 0 or when all potential missing numbers are already included in nums, some solutions fail to handle these scenarios appropriately. Explicitly accounting for these edge cases ensures your solution is robust and handles all inputs correctly. Another common oversight is neglecting to sort the input when it's necessary for your approach. Sorting simplifies the process of identifying missing elements, but skipping this step can lead to incorrect results. If your solution relies on ordered numbers, make sure to sort nums first, which adds O, n log n, to your complexity. Additionally, mismanaging indices during iteration is a frequent source of errors. For example, when appending numbers dynamically, it's easy to forget to update indices properly, which can lead to infinite loops or incorrect outputs. To prevent this, carefully manage your index updates and ensure your iteration logic is robust and well-structured. Understanding the broader patterns behind this problem can be very helpful, especially in an interview setting. Problems involving missing or duplicate elements often benefit from tools like sets, Boolean arrays, or sorting. Recognizing when to apply these techniques can make a big difference. Additionally, you should be prepared to discuss trade-offs between brute force and optimized solutions. While brute force methods may be simpler to implement, optimized approaches like using sets are faster and highlight your ability to think critically about performance. Another key area to focus on is edge cases, such as empty lists, large values of k, or inputs where no numbers are missing. Testing for these scenarios demonstrates thoroughness. Finally, be ready to explain the time complexity of your solution. For example, optimizing from O, n*k, to O, n plus k, shows a significant improvement and is something interviewers value. If you want to deepen your understanding of this problem, there are several related LeetCode problems worth exploring. For instance, problem 268, missing number, asks you to find the single missing number in a range from 0 to n. Problem 645, set mismatch, involves identifying one duplicate and one missing number in a range, which is another interesting variation. Problem 448, find all numbers disappeared in an array, tasks you with finding all missing numbers in a range from 1 to n. Lastly, problem 41, first missing positive, challenges you to find the smallest missing positive integer in an unsorted array. Each of these problems builds on similar concepts and helps reinforce the core techniques used in solving this type of problem. There are several alternative approaches you can use to solve this problem, each with its own advantages and trade-offs. A sorting-based approach, for instance, involves sorting the array first and then iterating through it to find missing numbers. While straightforward, this method has a time complexity of O, n log n, due to sorting, which may be less efficient for large inputs. A set-based approach, on the other hand, stores all numbers in a set and checks for missing numbers up to the required maximum. This method is faster, with a complexity of O(n plus k), but it requires additional space for the set. Another option is the Boolean array approach, which marks all present numbers in a Boolean array and then identifies the missing ones. While this method also has a complexity of O(n plus k), it can be space-intensive for large ranges. Finally, in specific scenarios, a mathematical approach may be applicable. For example, using the formula for the sum of the first n natural numbers can help identify missing elements efficiently, with O(n) time an O(1) space. However, this method is limited to cases where the input conforms to certain patterns. Great work! To wrap up, we summarized the key points of the append k integers with minimal sum problem, including the main algorithm and its complexity. Keep practicing to sharpen your problem-solving skills, and don't forget to like, share, and subscribe to stay updated with more solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!